All right, so we're going to do this graphing activity for uh, rotational kinematic motion. Okay. Now, I found this activity in some NIMSY files. It's supposed to be like a card match. Like, oh, here's a bunch of different theta versus t's. Here's a bunch of omega versus t's. Here's some alpha versus t's, and some scenarios. Okay. I want to modify this a little bit though. Okay. What I'm going to do instead is just let's pick the omega versus t's, and then see if you guys can draw the um, graphs that would go along with those, the theta versus t and alpha versus t. Does you guys see this? Okay. I see omega versus t. I see that. Okay. So the visual that you guys should have in mind for all these graphs that we're doing is some version of a rotating disk, right? Okay. Now, if it's going to constant angular velocity, actually, that could be this right here. Right? You guys see it? Angular velocity omega versus time is constant. Right? That could be this right here. Right? Or if you define counterclockwise as positive direction, maybe it goes like this. Right? Some of these maybe they're speeding up. Some of these maybe they're slowing down, coming to a stop. Okay. Some of these might even reverse direction. Maybe they're going one way and then they slow down and go the other way. Right? But something to do with like a rotating disk. Okay, you guys got that? All right, so first one. Oh, right, so you guys get your notes out while I was switching over here. Okay, we're just going to do a bunch of graphs. Okay, so let's make 3 sets of axes. Right now, I don't know, it's going to go like positive, negative exactly, but you guys know it's going to be theta and radians versus here. I'll help you guys out with the first one. I'll just make this type axis versus time in seconds. Okay. It's going to be omega and radians per second versus time in seconds. There's going to be alpha in radians per second squared and versus time in seconds. Okay. Okay. So the first graph, yeah, I'll break out the pink ink for this. It's like a red line there. Okay. The first graph says this. Okay. I want you guys to go ahead and draw 2 graphs for theta versus t and alpha versus t that could correspond to that. Could correspond to that. All right, so you guys know that's constant angular velocity, right? So it's just rotating at a constant rate, kind of like the Earth spin, right? The Earth rotates at a constant rate, for example. Okay. Right. Now, this last graph, there's only one possible answer you could have. Okay. And what does that look like? 0, right? So at the 0, right, there is 0 angular acceleration. That's always true for constant velocity, isn't it? There's 0 acceleration. Okay. You guys got that? Okay. Now, isn't it also true that the slope of omega versus t tells you alpha versus t? And there's 0 slope here. Yeah. Or if you want to go the other way, you could say the area under the curve of alpha versus t tells you the change in omega versus t. Right? So the fact that this is like 0 area means that there's going to be 0 change here. It's all true, right? Right. Do you guys have theta versus t? Right. Now this one, there's actually lots of things you could have done. Probably the most straightforward. If you started from rest, what would it look like? Yeah, it would look like could look like that, right? That's probably the most straightforward thing you could have done, right? But that's not the only thing you could have done. Right? Let's look at these cards right here. Would that work? This right here, that curvy line? No, not the curvy line because there's an acceleration there. Right? No. Would that work? Would that also be consistent? Yes, it would. If you drew that, then you're fine. That could correspond to this right here. Okay? That could be your. Okay. How about how about that? Would that work? Yeah, because look, the slope is the same everywhere, right? Just like this. Okay. So what this would mean is like if you had defined it being in negative direction and it's rotating, it's just doing its thing, da 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 da. And at some point, like crosses the finish line, and then just keeps going. Right? Sort of the linear analogous is like, let's say there's a point here, and we're going to call this point 0. Okay? You're in negative territory, you're just walking da 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 da. You don't change how you're walking. You just went from negative territory to positive territory. Right? That's the linear analogy to that. Okay? That one's curvy. No, no, no. Okay. You guys get that? All right, let's do next one. Right, so some axes going. Theta, omega, alpha. Okay, let's see what we got next. Ooh, on right there. So this is omega versus t, right? Omega versus t. Okay, time axis. Ink, ink. Omega versus t. All right, can you draw alpha versus t and theta versus t for that scenario? All right, let's go through this. All right, did you guys, what'd you draw for alpha versus t? Yeah, exactly. Just a negative constant value. Right? So everybody has to have something like that. Right? And slope of this represents right, negative value there. It's constant. It's negative. Right? Or if you like the area of this rectangle, the fact that it is negative means you're subtracting angular velocity. Right. Now, what about theta versus t? Let me just put time axis down here. That theta versus t. Let's suppose it starts at 0.0. Right? Doesn't have to, but if it did, what would the rest of that graph look like? Yeah, kind of curves and bends down, maybe like concave down, you could call it. Right? Although it's still here, guys. Is the velocity always positive? The velocity is positive. The acceleration is negative. Right? So here's a way to think of it. What if I split this into like 3 intervals? Right? During the first interval, ooh, look at all that area it gained. That's a lot of displacement. That's like it went this far. During the next interval, now it went like this far. And then the third interval, yeah, it's a little tiny triangle. So I think as much. Right? So some version of that, right? In fact, if it goes to 0 angular velocity at that time, then this would like flatten out to 0 slope just as it's reaching the endpoint, wouldn't it? 0 slope. Okay. Let's look at the choices they have here. Okay. Well, that one bends up, so it's not that one. Ooh, guys, could it be this? Could that work? Yeah, that could work, right? Because you don't actually have to have it start at 0 location. You could have it start up here. You could have it start down here. That works, right? Uh, I know half you guys are in calculus. You guys have done integration by now, right? Right. You guys know if you integrate, you always do that like plus c at the end. Right? That's like what the plus c is, right? Like here I have like plus 0. It's the most straightforward thing. But here you can have like a negative c value. Just strip this whole thing down. Look like that. All right, what else we got? No, it's been in the wrong way. Ooh, could that work? That could also work. Right? That would also work. Just I got a plus c, it's positive. No, no, okay, we're done with this. All right, let's try. Stuff we've got here. Try to find a tricky one. Uh, here's the last one we do today. Let's try this guy. Okay, I'll walk through it with you. And so we got an omega versus t that bends up. Yep. Right. So alpha versus t, right, would have to be a positive constant value, right? Just like that. Right? And theta versus t, let's see, I'm gonna do something like this. T. Oh, it looks like during the first interval, it was going in the negative direction a lot. Okay. And then it's like slowing down in the negative direction. Okay. And then it gained a little bit of positive, and it gained a lot of positive. So I'm thinking omega versus is theta versus t, angular displacement versus time. It's probably gonna be some version of that. Okay. Hey, you guys see zero slope here? You see zero coordinate here? Those would have to align, wouldn't they? Just like that. Right. You guys good? All right. So yeah, we got Friday and Monday. I'll get some more rotational activities, and yeah. Then oh, quiz on Tuesday. You guys know where's oh yeah. You guys remember quiz on Tuesday, right? All right, you guys have a great day.